Good afternoon, everyone. I am Sicheng from East China Normal University, Shanghai, China. What I bring to you today is our latest work GraphDecoder published on TVCG, which extracts the original data of diverse network graphs. Network graphs are actually everywhere in life, and we have been exposed to them since childhood. I do not like this kind of math problem the most when I was a kid, because it was difficult to find the answer, and search engines couldn't understand graphs. Later, when I got to university, I needed to draw a rotating balance tree for data structure. I also learned to draw an ER diagram before modeling the database. When doing projects, I need to draw flow charts according to templates. When taking notes, I want to convert mind maps into notes. I was faced with the process of converting graphs into data all the time. So how to convert a bitmap into original data is the core of the reverse visualization project. For some basic chart types, such as bar charts, pie charts, line charts, etc., there are already many mature inverse visualization works to extract their original data. Last year, our group also published a work to extract the original topological data of simple network graphs, but it was limited to solid circular nodes and straight connecting lines. This year, we have expanded the scope to more styles of network graphs. This method is suitable for hollow nodes, nodes of different shapes, curves, polylines, and text information. We first use OCR to extract text information from the image, then use an attention mechanism semantic segmentation network to segment and obtain the semantic label of each pixel. We finally use a heuristic method to restore the original data of the network graph. Since the task of labeling relational graphs requires a lot of labor, we used a generated dataset as our training set. We controlled a variety of random variables as much as possible, including node position, number, shape, fill and border color, length, thickness, curvature, bend, color of the connecting edge. We used D3, scikit and data augmentation respectively for a total of 12,000 training sets. In the semantic segmentation model, we found that the most challenging thing is the segmentation of edges, because it is ambiguous with the border lines of hollow nodes, and it is thin, so it is easily lost or broken in the segmentation results. In this regard, we have made 3 improvements to the model. The first is to increase the parameter weight of the edge in the loss function. The second is to use the attention mechanism of the attention gate for pancreas segmentation to improve the segmentation of the edge accuracy. And the third is to reduce the feature loss of edges in excessive convolution by simplifying the backbone network for feature extraction. It can be seen that our results have been improved in the segmentation of edges and long nodes comparing with the prior works. We used an ablation experiment to prove the effectiveness of each operation. After obtaining the semantic segmentation results, we traverse the pixels surrounding the connected components of each pixel identified as an edge, and judge the connected components of the 2 node categories with the largest number of pixels traversed as connected. Our method can be applied to recover images that have lost their original data. Users can also extract the original data from images and modify the chart to reduce the workflow.
Finally, the mind map should be the DNG you are most familiar with, because almost everyone has used it. You can also switch the color schemes, which are dark, light and default. If you don't like our preset themes, you can also customize various attributes in the control panel, including the type, width, and height of the node, the font size, color of the text, and so on. You can also modify the thickness of the edges. Certainly, you can also modify the content of the mind map at any time according to your inspiration. Or you can change the layout of the mind map. Everything is up to you.
In addition to electronic images, our method can also be applied to some hand-drawn sketches. Designers only need to draw a sketch of the graph on paper, take a photo and upload it to GraphDecoder to automatically convert it into an SVG rendered graph.
First, you can draw on paper, give full play to your artistic talent, and boldly use different colored brushes, nodes of different shapes, and lines of different thicknesses. Then, just use your phone to take a picture of your masterpiece of art. After uploading the hand-drawn sketch to our system, an interactive visualization was born. Of course, our system.
We used a questionnaire to demonstrate the accuracy of our method in different aspects of data extraction for different types of graphs. At the same time, 5 pairs of results of manual data extraction and automatic data extraction were designed for users to score. The results show that our method is very close to the results of manual extraction. We also evaluate on a real dataset of 100 images using 2 metrics, structural similarity and perceptual similarity, and the results show that our method outperforms prior works. In order to prove the robustness of the method, we also generated images with 3 different resolutions and graphs with 3 different numbers of nodes, a total of 9 sets of generated data sets to evaluate our method. The results show that our method performs well on images of different sizes and at different scales. To summarize, we propose a method to extract raw data from diverse network graphs, and use the attention mechanism to improve the model accuracy of semantic segmentation models. For some complex machine perception tasks, it is a good method to imitate the process of human understanding of visualization. Our pipeline extracts data from graphs in 2 steps, which imitates how humans understand graphs by first obtaining global information and then restoring local information. During the try-and-error process, we also found that most existing semantic segmentation models are suitable for natural images. Most of their segmentation targets are large targets, such as people, cars, trees, etc. The location and category of these targets are the most critical things. However, in visualization images, the shape and size of targets are also very important, and some models of medical image segmentation may be more suitable for this type of segmentation task. Finally, we found in the error analysis that because the training set is often some images that meet the design standards, for example, the starting node of the flow chart should often be an elliptical node, and the starting node of this input picture is a rectangle, in the segmentation results errors have occurred, and we believe that some non-standard relationship diagrams can be automatically corrected through these error analyses in the future. That's all. Thank you for listening my talk. Welcome to further discussion by email.